Hello everybody. Welcome to the Data Platform Summit 2020 session about building high-end SQL Server infrastructure. In the following 60 minutes, I'm going to talk about how to build servers that can run extraordinary workloads, very high-end workloads at a reasonable price. Few words about myself. My name is Thomas Grohser. I'm with SQL Server for a very long time, almost 26 years, and I've contributed to several books, and I'm usually working with corporations that have high-end demands. Yes. For the last 11 years, I'm a Microsoft MVP for SQL Server first and now for Data Platform. Coming back into the picture. So, before we start the whole thing, a little bit fun to begin, but there is some importance to that concept. We have to learn how to compare stuff. If we build high-end infrastructure, we have to often test stuff out and have to compare. The problem with comparing is, in many cases, you have to compare apples and oranges. And it's because every vendor builds every product different, and sometimes this is on purpose, and sometimes there's legal reasons for it, but it's really hard. Yeah? And it doesn't make it easier if the products blend into each other or overlap in certain things. And sometimes one product is disguised within another one. And software, hardware, everything plays in. And even if it's a clear-cut difference between two products, something like this can happen, and I usually refer to it as marketing, that some people explain it very differently, and you think you have an apple and an orange, but in reality you might have something very different. So, how you design high-end systems. Is the very first thing is you have to have a service level agreement. If you don't have an SLA, you engineer against a moving target, and that never works. I've unfortunately, trust me, I've tried it, it doesn't work. You need to sit down with your business, come up with the requirements, how much can you be offline, how much data can you lose, how fast has the system to be, how many hours per month, per year, per day it needs to be available, how much downtime do you have, how much maintenance time every week, every month, and how much data can you lose. That's one of the most important ones. Yeah? So that's the first thing you have to establish, and many, many more, which are mostly then blending over into the operational part. But unless you have an SLA, you don't know what you're engineering for. So that makes it really hard. Then you have to remove all the marketing seeds that marketing placed in your head. Yeah? Because, yes, every product is the best, but maybe not for the case you need it. Yeah? And no company will ever say, we make a crappy product, so let's not buy it. Every company says, hey, we are the best. And then they give you a reason why. Yeah? And you can always look at three different ways and limits, and in some way, everything can be number one. Yeah? Another one is don't let tradition limit you. Just because we've done something a certain way for 10 years, we have to keep doing it. Yeah? Sometimes it's time for change. And sometimes it's good to keep with a working system. But every couple of years, there is a new technology, there's a new way of doing things that might require you to completely upside down what you did. Yeah? For databases, that point, the latest point for that was the invention of flash SSD storage. Yeah? For 50 years before, everything was to optimize data on a spinning media. How can we get it on and off that spinning media as fast as possible? What can we do? And now it's a whole new game with SSDs, NVMEs, persistent memory, all the nice stuff we're going to talk about in the next hour. Yeah? And keep it simple, stupid. Yeah, a very old system called KISS. If you build something that nobody understands and nobody can operate, there's no point, yeah, because it will fail. It has to be as simple as possible. And what I've learned over the years is the more tools you stack on top of each other and the more vendors you stack on top of each other, the worse it gets. Once you have the SLA, you have to translate them into engineering principles. What do I mean with that? What I usually do is I have my core engineering principles. Yeah? Data consistency and correctness is the most important one. Recoverability is the second one. Availability is the third one. Performance the fourth. Security the fifth. And maintainability the sixth. What does this mean? If the SLA tells me to order my engineering principles in this order, this means I will rather lose data than have incorrect data. And I will rather go offline than not be able to maintain data. Yeah? So this has the higher priority along the system. Yeah? And the last one is, yeah, if we can make maintenance easier, that's great, but it's not an important thing, or security in this case. And a different SLA will give you a different list of priorities between these engineering principles. And you can add your own that are more important. Yeah. In this case, security is more important than anything. So we rather have incorrect data than have the data stolen. Yeah. Or accessed by someone who should not do it. Yeah? And again, this is defined by the SLA, not by you, and in every place. And for probably every application or every database, this might have a different order. And that's good. And once you have that, you print them out, put them on the wall, and every time you have to make a decision, for example, between security and recoverability, you know, if you're running in this way, that's more important. In this case, it would be the other decision. This makes it super easy to go along because you don't have to make the decision, figure it out every time. You do it once with the SLA, come down, and then run. Good. So let's debunk some myths, because this is the biggest. I picked three. There's hundreds of them, but I picked three major ones that I pretty much have to explain away in every time I start helping a new company. Failover cluster instances do not increase availability. They're not. It's just a myth. Yeah. It was the case many years ago when hardware was constantly failing. Hardware is not failing that often anymore. It's much more often that software fails. Also, failover cluster instances introduce complexity to the system that causes extra failures. But that aside, you gain availability by having multiple nodes, but you can achieve that in many different ways these days. Yeah, you can have multiple nodes without having failover clusters. But you lose availability to do slow storage because failover clusters require you to have network attached storage. And network attached always means you're limited most likely by the performance of the network or the storage array behind it. Let's have an example. You have a server and normally it takes 4 hours to repair it. You have all the spare parts there, you have a person in the data center, something fails, person walks there, pulls the old one out, pulls the new one in, restarts the system, easily repaired within 4 hours. That gives you 99.95% availability on a single server, or the famous 5 nines if you take 2 of these servers and make it a failover cluster instance. Super simple. Yeah? We're not calculating network availability, storage, or whatever. We give it just the 2 nodes. And if we add storage availability, it would actually go. So now we attach a 48 terabyte database. And yes, this is a talk about high-end software. If you have a 5 gigabyte database, that's a different story. But with 48 terabytes database on direct attached storage, we can read and write at 36 gigabytes per second. SAN on a cluster, if you're lucky, you have 2 gigabytes per second, maybe 4, but that's already like super extra special configuration very few have. That means it takes me 40 minutes to restore these 48 terabytes, or 12 hours on our cluster. It's these days much more likely that a database needs to be restored for whatever reason than it is that a server will actually fail. If I combine these two availabilities, within 1 year, let's say we need one restore and one hardware failure, then our single server will actually have the better availability. Okay? So failover clusters were a great tool in the SQL 2000 area, maybe in SQL 2005 still. These days, especially SQL 2012, with introducing always-on availability groups, they lost the majority of the use cases. Next one. SAN storage arrays are faster and more reliable than direct attached storage. Also not true. Yeah. SAN is a management tool. Storage networks are a management tool for convenience, not for performance or reliability. They have decent performance and they have decent reliability. But what I always see is when people compare, they compare a $1 million storage array to 4 hard drives. That's not apples and oranges, as we learned at the very beginning. That's apples with panda bears. Yeah? That's not even remotely comparing the same thing. If you take $1 million storage array and you say you have it on 4 servers, then you take the $250,000 and then you put $250,000 in direct attached storage, and then you compare. Yeah, apples and apples. Yeah. Storage arrays are great if you need snapshots, cloning, deduplication, all these features. But if you need raw performance, you always have high latency through the network connection, and there's nothing you can do about it. These cables exist. The data has to pass through. Yeah? The switches in between have to. Could you remove the switches by directly connecting the storage system? Yes, but then why bother with it? Yeah? You have limited bandwidth because all these storage systems, they don't really scale anymore. They scaled with hard drives, and back then it made sense. Instead of putting in each server 100 hard drives to get the performance you needed, you put 500 hard drives into an array and then shared it among 50 servers. That made sense. With flash-based storage, all these flash-based arrays, they're all CPU bound on their controllers. Yeah, the raw storage they have in there could do multi-gigabytes per second, and then it all has to go through the controlling heads, and they limit it down to single-digit gigabytes per second, which is just sad, but that's what it is. Yeah. Also, you have unpredictable performance because you're sharing with other systems. Someone else is doing a backup. Suddenly, that was not planned, and suddenly your data warehouse ETL load takes twice as long. Seeing it all the time in large storage systems. And the array is, of course, a single point of failure. Do they fail often? No, because they have everything redundant, and that's what makes them also very expensive. Yeah. So that's a second. Let's do one more. And that one is important for whatever we're building here. RAID will protect your data on an SSD. No, it will not. SSDs fail for very different reasons than hard drives. Hard drive failure were mostly mechanical. SSDs fail because of age or because there's a software problem. And the RAID will not help you in most cases. Especially not from wear level failures. What's wear leveling? Wear leveling is that you can write an SSD a certain amount of times. Yeah? And while in the very beginning this was a big issue, these days most SSDs, especially the ones for enterprises that you put into servers, you can choose how much you can write to it. Yeah? And I personally, even with very busy systems, had very, very rarely an issue with wear leveling. But a RAID will not protect you. Why? Because all modern RAID controllers modify the whole stripe of data that is within one RAID, the stripe across all the drives, at once. So they will read the whole stripe and they will write the whole stripe. That means if you, for example, have mirroring, have two disks, every time you write to them, you will write to both of them. That means they age and wear out at the same speed. And they will probably die within very, very close time. You can help yourself by swapping drives after a while between systems so that the times are different, or you buy a new system and then you take half the drives out, give the other half in. But that's not it. Just assume RAID is not going to help your SSDs from bare leveling. And the second one is corruption. And that is true even for the old spinning media. Yeah? Undetectable write errors happen about every 10 to the power of 12 to 10 to the power of 16 writes. That's rare. But in today's tera and petabytes of storage, that means it happens about once or twice a year. What's an undetectable write error? It's something you write to the disk, and for whatever reason, a couple of bits flip so that the checksum is going to be exactly the same as before. And that's why it's so rare, because these checksums are calculated very, very good these days. But still, it can happen. And then, reading back from the RAID, again with a RAID 1 mirroring, it flips the bits on one drive, it doesn't flip the bits on the other drive. If it flips them on both, the data is corrupt anyway. But if it flips on one and the other, both have a correct checksum. Which one is the correct one? You might be able to do so, but the controller cannot, which is the correct one. So you need at least 3 copies or multiple checksums. And there's very, very few RAID systems that actually allow you to do that. So after these 3 myths, debunking these 3 myths, the approach I'm taking for the last 7-8 years to treat the servers as commodity and things that can fail. And this is very aligned the way the cloud works. In the cloud, if a server dies, nobody's going or rushing there to repair it. No, the services are just transitioned to another system. And you can do the same thing on SQL Server by using always-on availability groups. And thanks to the change in licensing, you can now have 3 copies of the data, as long as you're only using one, without extra licensing. And that allows you to build a lot of availability on the SQL level, while you can keep the hardware underneath very simple, very fast. And for the things we just talked about, the corruption and all that, SQL Server is really good in detecting that. And if you have always-on availability groups running on Enterprise Edition, SQL in many cases can just fix it by talking to the other nodes and getting the not corrupted data from there. So if a drive flips a couple of bits on a page, the other 2 copies can talk to each other, and they find out which one has the correct one and use that one going forward. So, recap. If you have a server that has a certain amount of CPU, let's call it 1x, certain amount of memory, and a certain amount of network, you connect it to a storage array with a certain amount of I/O capacity and latency, you have your base system with performance of 1x. And let's see what people try to do to get to 8 times the performance is. They give it 8 times the CPU because they think that's the most important thing. And if you're lucky, you get like 4 times the memory because they put in a couple of extra memory sticks. Network rarely gets updated. And when you look at the capacity, of course, that goes times 8 as well, because if we have 8 times the CPU, we must be able to do 8 times the amount of data. But we're only giving you twice as much capacity or throughput to the storage system, if you're lucky. In some cases, not even that happens. And of course, the latency of the storage system is going to be exactly the same as before. So if you do this simple math again, instead of for 8 times the performance, we only have 4 times, for 8 times the capacity, we only have 4 times the performance. That means by trying to make the system 8 times as big, we made it half as fast as it was before, maybe even slower. Yeah. So this is definitely not the way we should do it. And in the rest of the talk, we're going to talk how to avoid that. So let's throw this away. Which hardware tools do we have in our pocket that we can play with and make things super efficient? We have CPUs, which have a clock speed, we have a core count, we can vary that. We have L1, 2, 3, 4 caches and on the CPU. And I refer you to all the talks from other people on how to select the right CPU. Yeah? I will cover it briefly, but in my opinion, the CPU is not the most important thing. It's important, but if it does a decent job, we're good. Memory, type, DRAM, persistent memory, NVDIMMs. There's a lot of things. The speed, the higher is better. The quality, the cache value, the lower is better. Doesn't make sense if you have faster memory and then it takes many, many more cycles to get data in and out. Yeah, because the speed, the duration of a single cycle and how many cycles it takes to get to the data are working against each other. How many channels has a CPU? And my recommendation is always, if you don't fill all the channels, don't bother even trying to be fast. And we have non-uniform memory access, and we will use that in later a lot. Network, various different performances these days. And what I've learned recently is, while many years ago the difference between a 1 and 10 gigabit Ethernet was like $25,000 per port, today it's less than $10. And going to 100 gigabit Ethernet is probably another $200. Yeah? So high performance network is not that expensive anymore. And storage is these days NVMe drives, direct attached through switches or direct attached. And we have a couple of software tools: CPU Affinity, IO Affinity, persistent log buffer, hybrid buffer pool, and soft NUMA. And we will go through when these make sense and when not in our 4 examples that we have. So, legacy storage that you should not use anymore. At the beginning, they were rotating hard drives. Then they were put into a RAID in your server. Not doing this anymore. Then they were put in an external chassis and had the RAID inside that chassis. Then this was attached now no longer direct with SCSI cables, but through network, and was called SAN, stand storage arrays. Someone then figured out that these rotating spindles are slow, and back at the time, all they could find was memory. So they put up to 1 terabyte of memory into a box, which was insanely expensive, but it was faster than the spinning drives, especially for reads. Then a company finally put these memory and used flash storage and put it on a PCI Express card so we could plug it into the servers. We all know now how fast our laptops became with SSDs when flash storage was just replacing the spinning hard drive. Then these SSDs were taken into flash arrays and made the replacement for storage arrays that were using spinning hard drives. And some of them are great, and there are still use cases for them. But what we have to keep in mind is the first hard drive was 40 megabytes and could read 5 megabytes per second. Not bad. These flash arrays, they're about 1 petabyte in size or even larger, and they can read 8 gigabytes per second or write about 2 gigabytes per second. Sounds really fast compared to the 5 megabytes, but if you take the size increase into consideration, it took about 10 minutes to read or write these 40 megabytes on that individual hard drive at the beginning. It now takes about a day and a half to read or write the petabyte of that array, especially writing it. Reading is much faster, but still, it's hours and hours because they have a lot of capacity. Capacity grew much faster. And that's still true for a single hard drive. If you buy a 16, 20 terabyte hard drive, you can no longer read or write it in 10 minutes. It takes hours to completely fill it or read it. Yeah? That's just the problem, that capacity grew much faster than performance. This is why I call this legacy storage. Legacy storage is bound by performance. Current storage is NVMe, either in form of disks or in form of PCI Express cards. And the disks are also PCI Express. They're just in the shape of a disk right now. NVDIMMs is literally memory that has a battery attached, so that when the computer is turned off, the memory keeps the values that are stored in it. And persistent memory is a new invention from Intel. That is memory that just doesn't lose the data, but doesn't have the limitations of flash drives that you can write only a certain amount of times to it. This is what we're using now. Why? Because latency is measured in microseconds and nanoseconds and no longer in milliseconds. So the latency to write to it is much faster, and reading. And secondly, if you look, we will see later on a system where we put a petabyte of these NVMe drives into one box and we can read it in about 70 minutes, not a day and a half. Yeah? If we put data on persistent memory, we can read about 24 terabytes, which is the maximum you can put in a system, in about 300 seconds. So that's pretty fast. Or the 1.5 terabytes of NVDIMMs that we could theoretically put in a server, which nobody would ever do, is we can read the 1.5 terabytes in about 3 seconds. So that's what we have. So scaling up, you must scale all the dimensions. There's no point in just scaling the CPU. You have to scale memory, you have to scale network, you have to scale storage, both capacity, throughput, and latency. If you only scale some of them, you move the bottleneck immediately to the component or the dimension that you did not scale. This is just a fact. So let's go through our examples. We will have a total of 4 different systems that we're going to go through in this talk. The first one is the lowest latency OLTP system that you can build. The second one is high throughput data warehouse, high concurrency OLTP, and a commodity server in mixed workload. So I will try to basically build low latency, high throughput, high concurrency, and a mix of all of the above. We're not going to do it in this order, but these are the 4 we're going to go through. And I give you ideas where to start, and how to get there. So, low latency server, OLTP workload. This is for these workloads, most likely third party, because if it's in-house development, you can kick your developers that just talk to SQL Server through a single connection, and everything depends on how fast this one connection does something. You can put in 1,000 cores and it's not going to be faster because it's always one query at a time. Yeah, they exist, and sometimes you have to deal. The lowest latency you get with a single socket, one CPU. The moment you put in 2 CPUs, latency goes down. And that's by design. The highest clock speed you can find, no hyperthreading, turn it off, just real cores. So there's nothing stopping a core from executing. You put as much cache in it, and you might get that by buying a more core CPU and disabling cores, which will push up the clock speed again, but gives you more cache. This is something you have to test out. I've seen very good results by taking like a 12 core and running it at 10 cores, or a 16 core running it at 10 cores, or sometimes running the 8 core at the speed of the 4 core, by disabling it down to 4 cores and then getting back to the same speed as the 4 core had. Okay? It's a licensing nightmare, but sometimes worth the performance. High performance RAM, high speed, low CAS values, and NVMe disks for I/O, direct attached storage. They're plugged into PCI slots so that you lose no overhead with cables and any kind of storage thing. And in case the machine needs writes are essential and you want to make them as fast as possible, you can use an NVDIMM for log writes. So let's build this. And you should use CPU Affinity, and we go through all this in the next couple of slides. So this is the block diagram for a single socket system with all the possible options you have. If it's an Intel CPU, you have 12 slots for memory, and you have 48 PCI Express lanes that you can use. What we're going to do is we put one CPU in it based on high clock speed, and we fill the box with memory. Every slot will have memory. This will give you the best possible performance and latency. And we put as many drives in as we need. The more drives we have, the more we can work in parallel. Thing is, technically, these systems let you put in between 8 and 10 drives into each system. 8 is easy. 10 needs some trickery with how the main board exposes the PCI Express lanes, and then we need a dual port network card to communicate with the outside. This is for reading and queries that read the best possible outcome that you can create. Yeah. If you take one of the memories out and put an NVDIMM in instead, you can make the transaction log go there and be much faster, because you don't have to go to a drive. The drives are fast, but that memory module is much faster. So, CPU Affinity. There's a GUI for it. I usually use the T-SQL commands, but what you do is you change that setting, turn it off, and then you turn it on for all the CPUs. What this means is that if a query starts on one CPU, it's going to finish on that one. And for low latency OLTP, this is the best, because SQL will never waste time moving workloads from one CPU to the other. Yeah? Especially if you have these single-threaded workloads, it's running on the one CPU. It doesn't matter. Keep going. Yeah? It just makes it a little bit faster for free. I/O Affinity. This is something that very few people use, but if you use it correctly, it can make your log writes insanely fast. So what you do is you have your CPU and you set I/O Affinity to one core of that CPU, one little core. Yeah? You affinitize I/O. That does not mean that all your reads and writes to your data files go through that one core. That just means the log writer, the part that writes to the transaction log, will always use that core to use that. Yeah? And that core needs to be on the CPU that has the NVDIMM connected. If you have a single socket CPU, that's very simple. That's the one you have. If it's a larger system, you have to make sure that you pick the right one. Yeah? That means that the log writer from SQL Server now can directly access that memory module if it needs it. The same CPU also needs to have either persistent memory or the NVMe drive connected that will have the transaction log file. So when a log write happens, goes into the CPU pushes it onto that memory chip, and the same CPU, if you affinitize the NVMe driver to the same core, will take it out of that memory and push it then to the hard drive. What most likely will happen that these two events are so fast that the data is still going to be in the cache of that core, meaning the data goes directly this way, but is committed the moment it lands on the NVDIMM. But it never has to read it from memory again. So you have one memory write, one write to the disk from the same cache. And that's the point of I/O Affinity. You have to turn that feature on inside SQL Server. That's an option for your database. So auto database persistent log buffer on, and the path to that DIMM that you have to format as a storage device. Good. Commodity server. That's the one everybody wants to use. That's your general purpose machine. I'm doing this second because it's a very simple step from the low latency to socket server. That's the garden variety database server that everybody should use. You don't need super latency, but you also don't need super throughput. You just need a solid, good machine that runs the majority of your workload. That's the 2-socket server. You might just do it with 1 socket with the latest generation of AMD because they're much more flexible in that way. But normally Intel, it's better to have 2 because you have twice as much memory and you have twice as much PCI Express lanes to connect storage. That's why I prefer the dual CPU for the things. Same block diagram as before, just twice. It's literally the upper half and the lower half are mirrored, and the same thing. Yeah. You have higher latency. Why? Because if this CPU needs to talk to that memory chip, it has to ask the other CPU for help. And the same goes if this CPU needs to read from that drive, it has to go through the other CPU and cannot go directly. Yeah. So everything's there twice compared to the single socket system. Twice the memory, twice the disk capacity, and twice the CPUs. You can build these systems now up to 128 cores on AMD and 112 cores on Intel. Yeah, this is a lot of cores. Yeah, not fun to license, but if you need them, they're big. But hey, 2 times 10, 2 times 20 cores is a nice machines that can push a lot of data. So yeah, 2 CPUs, you fill it up with memory as much as you can, and you put the drives on it, and you probably want to use more than one network card. You should use more than one network card. So that's the commodity server. The important part is that you balance everything between the 2 CPUs. So you have the 2 CPUs, you put half the memory on one side, half the memory on the other side, half the drives on the left, half the drives on the right, and the same with the network cards. This is important so that there is always a chance that whatever query you're running, the local CPU that it runs on can have all the resources it needs at hand to do so. It's not going to be always perfect, and sometimes it has to ask the other CPU for help. But if you build something like most vendors will give you out of the box, where all the resources, all the I/O resources are connected to the first CPU, just so they don't have to put in extra PCI Express rises on the main boards and all that, and they're saving a couple of cents on their hardware. Everything CPU number 2 does has to go through CPU number 1, except memory access. And I've even seen vendors giving you just memory on one of the 2 CPUs. This is like almost a crime. It should be a crime. But it what happens, yeah? So no to that as well, yeah? Everything needs to be half here and 1 half here. Yeah? Then you have a very balanced system. And SQL Server supports that actually, very good. So, away with the unbalanced systems. So, what if we need to build the highest concurrency OLTP workload you can think of? Yeah? How far can we go? Okay, we can take 8 sockets, meaning 8 CPUs with 28 cores each, and make this 224 cores. That's a good point to start. Yeah? When you connect 8 CPUs, you can't connect them all with each other, which would be perfect. So we even have higher latency here than we have before. But we have lots of independent cores that can work on independent stuff at the same time. That's why we are going for high concurrency. If you see this diagram how these CPUs are usually connected, so the problem is, as before, when we just had 2 CPUs like this and this, they could straight talk to each other through that one connection they have, or on a normal board it's up to 3 connections between them. Yeah? Now, if we have 8, some of the CPUs they can't talk to directly. So they have, for example, if CPU 0 wants to talk to number 7, it has to go through number 4. Right? And yeah, that's just the price to pay to have more CPU sockets and more CPUs working with each other. There's always a way that 2 CPUs can talk to each other with 1 hop in between, but there is at least 3 it can always talk to directly. And this is what you should consider when placing storage devices and connections to the outside network. So for example, if you team 2 network cards, make sure they are connected here and not between 2 CPUs that don't see each other directly, because these drivers have to talk to each other, and that's much more efficient if they can do it on CPUs that are right next to each other. This is the block diagram I use for the 8-socket systems and where I put stuff in. And I have good news for you guys. I've showed you these diagrams and they're always in a different font. Why? Because I copy pasted them out of a PDF that I'm currently creating. It's more like a book already. I'm writing a book on how to build this in details, and each one of these servers has about 10-15 pages in explanation how it's actually done with sample actual hardware from the real world. And it's not going to be ready today and maybe not this year, but I'm hoping in Q1 next year that this will be available. And good news, it's going to be available for every SQL Server user for free. This is for my gift to the community. I've spent many years figuring all that out, and it's time to share that. High concurrency storage, high concurrency system, the storage part. We need to make sure that every CPU can reach every drive. And this is thing is, so each CPU can see 4 other CPUs. This goes here, and the other 4 can see the other one. So what we have to do is make sure that 2 CPUs that see each other get 2 of these interfaces, and then the pairs go down. And this allows every CPU, with worst case one talking to one other CPU, to reach each and every storage system to pull a page from an NVMe drive. And that requires us to put in 2 PCI Express lanes, switches in between, to make sure that every node can talk to every node at a reasonable speed. This is not as fast as if we would just use the possible number of drives, but overall it gives it a nice low latency. It's not the perfect one, but good enough to deal with parallel queries against large data sets with high concurrency. So for data, we have 8 PCI Express connections with 16 PCI Express x16. We use switches, and then we have 64 drives, which are either 4 or 8 terabytes. There are 15 terabyte drives already available, but they're not as fast as the 4 and 8 terabytes. Best performance you get from the 8 terabyte drives. The data log we put on an NVDIMM if we need. Most of the time you might not. And we put 2 PCI Express x16 NVMe cards that don't have the switches to get to the lowest possible latency for the log file. And we do the same, 5 of these cards for the PCI Express for TempDB. NUMA, non-uniform memory architecture. In these high concurrent systems, this becomes very important. So what is NUMA? We have a network card that's connected to a CPU and memory. And then we have our database. And in a large system, we have many, many more CPUs and memory. And we're going to insert more network cards. And then we're going to kind of split our data into 8 different buckets. And then we let our applications, we redirect our application to the network card that is closest to the data. So for example, all the customer related queries could be redirected in our case to network card number 3. And then they would use the data that is most likely in the buffer pool on that node, on that CPU, from here. And then if we need data from our product catalog, we would connect through the other network card and thing. This is basically helping SQL Server through NUMA to keep the data as local as possible. Yes, we will have cases where SQL Server has to ask another node for data. That cannot be avoided. But if 80 or 90% of the queries can be satisfied in the local ones, it's great. Another way would be you take your customer base and split it by custom ID or something, modulo 8, and then rotate between the network cards. Yeah? It's basically helping SQL Server, like putting the highest level of the index into the application and making it go there. It's the same thing. You have a building with 8 rooms and full of filing cabinets, and you ask someone to find it, And the person can go into the first filing cabinet, and then he finds, oh, there's just a little index card that says, oh, this file is actually in room number 3. This is when you need to go through the wrong one. Yeah. But if you're already in the right filing cabinet and you know up front, like all customers with A to D are in room number 1, you know you go in there and you will find the data. And this is the same with NUMA. Soft NUMA, even more precise. So if we look at a single NUMA node, what we can do, the CPU has many, many cores in it nowadays. Yeah? So what we can do is, each network card, we can give an additional IP address or a port number that we affinitize through soft NUMA to one core and its cache. And then this will become an even smaller range of data. And we can repeat this for all the other cores that are on that CPU. So basically in our 8-socket system with 28 cores on each one, we could do 224 buckets of data, and we could have the application connect to the exact bucket where the data is, if we know it. With the advantage that if we don't know which data is, we can choose any of the connections and SQL Server will find it with us. And this is the difference between scale up and scale out. In scale out, you always need to know where the data is, or your query will horribly suffer from crosstalk of these servers. In scale up, if you know where you find the data, you make it much, much faster. But if you don't know what the data is, or sometimes you need the data of all your customers or all your products, it's still decent. Oh, that's what we can do with soft NUMA. Last example, high throughput data warehouse analytics workload decision support system. It's no longer important that many, many queries can run at the same time. Now it's more important that an individual query can hit as much data as possible. We're basically going with our 8-socket system again. Again, high-end. This is not... Most data warehouses will run just fine on our commodity server. If you need more, I designed one for 1 petabyte of usable storage. So the database, if you say space used, it will say 1 petabyte. Yeah? I'm using 256 disks, 8 terabytes each, 24 terabytes persistent memory, and 12 terabytes, 6 terabytes of regular memory. Full scans across all data is possible in about 72 minutes. So reading a whole petabyte data, summing it up, averaging it, everything that's not super complicated as a query can run in about 72 minutes, which for this amount of data is really good. Yeah? We're using 448 logical processors, which is the exact same configuration as before, with one difference: we are turning on hyperthreading. Because if throughput is requested, then hyperthreading makes sense. For latency and concurrency, not so much. This thing, same as before, has 800 gigabit Ethernet for fast loading, backups, restores. Basically, each CPU has its own 100 gigabit Ethernet network card. How are we moving these CPUs and connecting them to the storage? Each one has 6 of the 12 available memory slots filled with persistence memory. That gives us the 24 terabytes. And then we have 8 external storage boxes with NVMe drives. Same concept as before, where we had 2 of them. And we take 8 of these drives, 1 from each chassis, and we group them together into a volume. And this is just done by software. And the difference is that now we're not using 8 PCI Express connectors of 16x each. In this case, we use 16 of them. So each one of these chassis is connected to 4 of the CPUs, and that gives us a total of all 8. If we put that in, so if we take these stripes of 8 drives, we get about 41 terabyte with 8 terabyte drives on usable capacity on each one, and we have the 24 terabytes of persistent memory. First, we're going to configure TempDB, which is 64 terabytes in size, and that's its maximum size, and it cannot go above it. And this is done by putting 32 terabytes on each one of these 41 terabyte volumes. Theoretically, we can go higher, but if a query needs more than 64 terabytes of TempDB, we should rewrite it. And we give it 4 terabytes of transaction log in the persistence memory, so we can write ultra fast to TempDB. The actual database, 1 terabyte in size, 1 petabyte in size, gets a total of 60 data files up to 34 terabytes, and they are multiple because we're using file groups and partitioning to split the data up. But basically, the 1 petabyte is going to put 34 terabytes on each of the drives, which gives us another buffer of about 6 terabytes of growth if we need to go above the petabyte. But basically, once we reach the petabyte in size actually used, we will go to a larger system. And we added another 12 terabytes of data in the persistent memory where we put the lookup tables in. Not the dimensions, but the lookup tables. Those are the ones that constantly get joined so that they don't have to come from disk, and especially that they do not get pushed out of the buffer pool by scanning the large fact tables. And we put a constant size 8 terabyte transaction log also on the persistent memory. And again, no ETL load should ever create 8 terabytes of log, but if something goes wrong, there's some capacity there. So this is how these systems were created. Good. Special thanks to Microsoft for sponsoring and supporting the Data Platform Geeks and SQL Server Geeks, who brought this summit to you, the audience, and allowed me to speak here. There are 3 ways to win prizes. Thank you very much. Post your selfie, give session and conference feedback. I really ask you to do that because for the session, because that's how I know how I can improve. And if I forgot something, well, I guess, yeah. Visit the sponsor of the next video and follow the Data Summit on Twitter. As far as I know, there will now be a live session following this recording where you can ask me questions, and I thought during the whole time I already answered questions in the chat while you were listening. And of course, anytime later you can write me an email at tg@grohser.com and ask a question. I try to answer in a reasonable time, but I have a daytime job and sometimes it takes a little bit. Thank you one more time, and I think we will see each other live in a few seconds. Thank you very much.